Thanks everyone for attending my talk. I'm going to talk about probabilistic programming. I'm going to talk about rugby. I'm still suffering depression from a couple of weeks ago. And, and I'm going to talk about a model I built for the Six Nations last year. And I'm going to use this as an excuse to introduce to you Bayesian statistics and probabilistic programming, which are two things that I consider equivalent, although that's very loose equivalent, but they are generally used equivalently in the literature these days. And I'm going to talk about how you can use this as a nice framework, which I don't see too much at conferences like this, as a nice framework to solve a problem and to explain interpretable results. Okay, so I'm a data scientist slash blogger, and I need to find another slash, and I'm based in Luxembourg. I have a master's in mathematics, so I'm come from the statistics and mathematics side of the data science continuum. An ex-Amazonian. I'm an occasional contributor to Pandas and PyMC3, which is what I'm going to talk mostly about in this talk. I co-organized the data science meetup in Luxembourg. Who knew there was a data science meetup in Luxembourg? And I'm on Twitter. I give a long, in-depth tutorial about this stuff in PyData London, and that you can go to those slides, and all the code is there, and it's easy to reproduce. And another project I want to talk about, just to plug, is I've done a series of interviews with a number of data science thought leaders, including Hadley Wickham, and asked them about data science. And a lot of people find this quite useful as a way to talk about the different problems that we have in the industry. Okay, so I've simple aim of this talk: make Bayesian statistics and probabilistic programming not so scary. And I don't know if I'm going to succeed or not, but we'll see. Right, so the high level view is that generally in software engineering, you use variables, normal variables, i.e. they have no randomness in them. But probabilistic programming, you use a random variable in the statistical sense or probabilistic sense. Something that I think is really important is that they allow you to create a generative story, a story that you can tell people, like, these are your inputs, this is your model, and this is your inference engine, and this is how you can get an answer, and we can talk about this, and we can change our input as we get more information about the phenomena that we're trying to model. I consider it a different tool to machine learning, because generally, whenever we talk about machine learning, we're talking about things like SVM and linear regression and stuff like this. I'm not going to talk about the different paradigm stuff of frequentist statistics versus Bayesian statistics. That would take all day. Jake van der Plas has already solved this problem, and often I find that Jake van der Plas has already solved my problem. And I think a really important thing that I want you to take away from this talk is that probabilistic programming forces you to be explicit about your subjective assumptions. We are always making subjective assumptions in every model that we make. The famous dictum by George Box was, all models are wrong, but some are useful. And a lot of people don't get that, and a lot of our stakeholders don't get that, and a lot of practitioners don't get that. So I just wanted to ram home that point about subjective assumptions. So I'm going to start the talk by comparing this to machine learning, and I'm going to use Olivier Grizel's examples. Olivier Grizel is one of the co-contributors to scikit-learn, and he was talking about this, and I thought it was a really nice idea. You take data in, you have a black box, you get predictions. That is actually how most of us treat scikit-learn. Whereas with probabilistic programming, you still have a black box. Your black box is your inference engine, or your Monte Carlo simulations, if any of you have heard about these things. But your model is open. Your model is open, and we can talk about it. We can show people code, we can show people distributions, we can talk about these things, we can talk about what the shape is, we can make this explicit, rather than, here's a random forest, and here's magic happens, which unfortunately doesn't really work in some industries, and doesn't really work in places that don't want to accept just trust the machine. So I study mathematics. It's a hard area to do Bayesians by pen and paper. Thankfully, there was the invention of Monte Carlo simulations, and these simulations are used to approximate your likelihood function. Now, I've introduced a little bit of notation here, but I'm going to explain this in the next couple of slides. And of course, some of you are feeling a bit like this. But don't worry, it will not be this scary. Right, so this is Bayes' rule. And he was reverend a few hundred years ago, and he came up with all these probabilistic rules. So we have a prior, and the prior is the thing that you put in to your model. The prior is the thing that you pick. The prior is the thing that is subjective. But the prior is the thing that you are being explicit about your subjectivity. The likelihood function is what you want to simulate. You want to simulate your likelihood function using Monte Carlo methods and all these wonderful things. And you want to get out your posterior. And your posterior is the thing that comes out of your generative story that tells you what is going to happen in the future. So, the Quantopian blog is a really good blog. For those of you who do not know, Quantopian is a crowdsourced hedge fund. And I don't know what that means either, by the way. But they have a really cool financial platform, and they allow algo trading. And a lot of the stuff they do is they use Bayesian methods to look at who is better and who is worse in trading strategies and what trading strategies work. And they use all these kind of things for risk models and stuff like this. If you're looking for really thorough examples of probabilistic programming, it's one of the best things to go to. And this is one of the examples that was on their blog that I thought was really interesting, right? So you have your two parameters, you have your mean and you have your variance. And these are your priors. And these priors go into a Bayesian model, right? And this Bayesian model also takes in your data, right? Your returns data. So this is a financial example. But this data could be anything. And you're going to see this example when this is rugby data. Or it could be anything. Okay, so then you pull in these priors. And the priors are the things that you've picked, the things that you've decided on, the things that you think that the model should have, right? And you can pick them in all sorts of different ways. Sometimes you just pick a normal one and hope for the best. That's generally my strategy. Sometimes you have domain-specific knowledge about a certain phenomenon that you're looking at, such as sports. We know that scoring distributions are mostly possible. So you put this in, and you have your returns data or whatever data you want, and it goes into your black box and into your model, so your open box model, which you run with a few black box things in the background. And out comes your posterior. And that's it. That's Bayesian statistics. We can all go home now. Yeah. So, of course, those of us, I used to teach, by the way. I used to get this a lot. Math, what's it for? So, when are we going to use this, sir? So, okay. But who knows, what if math was actually useful in the real world? So, I know there's some of these guys in the audience, actually, and I know they're recently opened in Dublin. But Zalando is, for those of you who do not know, is a German-based e-commerce outfit. And they were using Bayesian statistics for automatic weight estimation. And that sounds kind of like, why would they do that? But from the sounds of things, it worked very well. And also, automatic weight estimation of clothes is a really big problem in e-commerce. It's a really hard problem to attack with normal methods. You have some sort of internal domain knowledge that you picked up just from talking to people or understanding what the phenomena is, and you can simulate. And the other thing that is really nice about probabilistic programming is that you have uncertainty estimates. And the uncertainty estimates come out of your model, right? So all data is noisy. All data is wrong. And I can jump up and down all day and shout about this, but I won't. But we have to be honest about that. We have to be honest about the messiness of the process that we're engaging with, and use tools that allow us to be explicit about the messiness, uncertainty, and subjectivity. So this is kind of a side point, because this is something that came up in previous versions of these tutorials I've done. It's how do you pick your prior? And it depends. It's always a cop-out, right? It depends. But in some sense, it's a bit of an art. You generally base it on experience. And a lot of empirical results in the literature say things like, it doesn't actually matter. If you just have enough data, you'll generally converge towards the right posterior anyway, so who cares? Just pick whatever. So that's kind of my last explanation of that. So,
just on the prior bit.
yes. Not that I can think of off the top of my head. There might be. My understanding was that for certain problem domains, like clinical statistics, like clinical trials, we have some rules of thumb. I think we even have estimates there. But my understanding was it's always a bit fuzzy and always a bit subjective. And that's why I wanted to be honest at the start that we are being subjective, but we're also subjective in frequentist statistics. We're very often, most value at risk models assume that financial data, return data is normal. We know that's a load of rubbish, right? But we accept this, and we make decisions, serious decisions, based on this. So I hope that's not too much of a cop-out of an answer. It's the best I can.
It's cool. Yeah, no. Like, if you don't have an answer,
Yeah. Yeah, no, John D. Cook is like one of the leading experts in this, and I asked him, and he's like, I don't really know. It's like, you've been doing it for 30 years. Yeah, but it doesn't mean I know. So these are my wonderful friends, right? They're called distributions. And these are the kind of things you can use for priors. So in my rugby analytics example, I used the gamma prior for home scoring because for home attack because it kind of worked relatively well that over a time frame you're not going to have an increase in scoring, you're going to have like a decrease in answers of scoring.
This is for continuous.
This is all continuous. Everything's continuous. I would say that reality is continuous, but I have a physics degree and I'm not sure anymore. So and then another thing that comes up if you deal with people in the statistics community is to say, well, isn't probabilistic programming just Stan and bugs? For those of you who do not know, you're lucky. So Stan and bugs are specialized statistical software. Stan is done by Andrew Gelman's group, and Andrew Gelman is one of the leading lights in Bayesian statistics. He's at Columbia. There are interfaces to this in Python, but one problem you have is that you can't use the entire functionality of the PyData stack, right? So you can do stuff in pandas, and then you have to pass it through a kind of API, and it changes everything, and you don't get the same flow. I find it a very restrictive workflow. There's an in-depth discussion on Jake van der Plas's blog, and I linked to it at the very last slide, when he talks about frequentism versus Bayesianism, and he uses PyMC2 in this. I'm going to use PyMC3 in all my examples because I like to use stuff that's new and shiny, and but also I'm a contributor as well. And for those of you who were at the Theano talk by Paul earlier on, one of the really interesting things, which is interesting both practically and intellectually, is that Theano is like the backbone of PyMC3. So it's entirely written in Python. So we're not like outsourcing stuff to old Fortran libraries. We're using GPU speed up, we're using automatic differentiation, symbolic differentiation, and we're using this to compute the gradients because a lot of what you're doing whenever you're doing these computations is effectively becomes linear algebra. But I would say something like that, right? So no, in Python you have PyMC3, which I've already said. It's a complete rewrite of PyMC2. It's now in beta status. It was it's based upon Theano. It's got computational techniques for handling gradients, which is one of the reasons why they decided to do an entire rewrite. It's automatic differentiation, GPU speed up. It's so much fun playing with GPUs. I just thought I brought that out there. It's also used in deep learning. So here's some of the links to the literature that is really interesting, right? So there's currently a project to port BMH, right? So no, I've used an acronym here. I shouldn't have done that. But this is Bayesian methods for hackers. And for those of you who don't know, Bayesian methods for hackers is now a book in print. I'm a contributor to the online version, but I'm not in print, unfortunately. And it's written by Cameron Davis and Pylon. And for those of you, there was a talk earlier on that mentioned Lifelines, and Lifelines is done entirely by Cameron Davis and Pylon. And he's a really good contributor to the community. And he basically wrote the book in the IPython notebooks, which, one of the first ever examples that we saw of an entire book written in the IPython notebook, or the Jupyter notebook, as I should call it now. And it's a really good introduction. So if you know a bit of math and you know a bit of code, you can use this, and within about a few hours, you'll be doing Bayesian models. And there's an entire port to write it into PyMC3. So if you want to use the new version, PyMC2 is somehow more accessible because there's more literature, but unfortunately you have to contribute to the literature to get the literature to a certain critical point. So there's always that kind of problem. I linked to this already. I did a thorough tutorial on this. I want to mention the 3 key authors of PyMC3. It's John Salvatierra, Thomas Vecchi, and Chris Fonisbeck. The reason is that they've done a lot of work. I think John Salvatierra actually gave up his job to work on this project, which is the kind of thing that we see sometimes in the open source community, but we don't really acknowledge. So unfortunately, none of this stuff comes for free. So cite it, contribute to it, put testimonials on the website, all these sort of things that I generally say, but I'm right. Okay, so I'm going to talk about my case study. I'm going to talk about rugby analytics. I'm going to talk about last year because Six Nations was better than the World Cup. And I wanted to build an understandable model to predict the winner, right? So I wanted to talk about the model. I didn't want just a black box answer. And the key info that I came up with, and that by reading the literature, because this is a studied thing. So generally what you find is this very interesting phenomena. Someone's doing a PhD, and for about 2 years, they're churning out papers, and then they stop their PhD and they go to work for Betfair or someone similar. So you always find like, oh, the guy's gone. So there's nothing, there's no more stuff coming out. So, and we only have 5 minutes. So I'm going to have to rush a little bit here, but we only have scoring data, which is noisy, and hence Bayesian statistics. So I'm not going to talk about this in depth, but it's all on my blog, and it's all thoroughly explained there, and if it's not, send me a pull request, or talk to me afterwards. So I picked a gamma as a prior for all teams. I use what's called a hierarchical model, because I didn't want the effect of home advantage to be distributed independent of the strength of team. I wanted to take home advantage into this model, because home advantage is a really important thing. From this, I was able to create a novel model based only on historical results and scoring intensity, and I simulated the likelihood function using a Monte Carlo Markov chain model, and per case sampler. In this case, it was a non-uniform NUTS sampler, which is one of the new ones. My data set was very small, so forget big data, I do small data. So, and here's the model. Because I'm running short of time, I won't go into depth with this, but this is basically, if you know a bit of math, this is really easy to explain, right? So this is normal. You've got a gamma distribution there. You've got another normal distribution here. You've got your team-specific parameters. You've got your home attack, and you've got your defense, your defense parameter. So you have 2 parameters there. You've got your home advantage is fixed, and it's applied over all the teams. So this kind of like will emerge. And the whole point of this is that you'll have an emergent effect, and from that you'll be able to rank the teams. And then there's a few more things here. And the important thing, as I said earlier on, is the likelihood function. We want to build a likelihood function for home points and away points. So you run the model, and this is how you do it. And I just wanted to show you that. If you want further details, go to the GitHub repository that I pointed to, where it's thoroughly, or there's other talks of me online. Right, so, and then from this, you get these kind of parameters, and you can talk about this. You can talk about home advantage, and you can pick, and Ireland and England and Wales kind of dominate this data set in terms of like the best attack and home advantage kind of things that come out of this, which is really interesting. So I did a simulation, and the simulation was that I got, that they would win, Ireland would win 4 games, so they dominated us. The reason I'm showing this was right. The rest of the model predicted that England would win the Six Nations, and this is why you should never gamble on mathematics. Oh, 3. So This is the wrap up. So what actually happened, incorrectly predicted. Ireland actually won by points difference. Thanks to the people who helped me with this. Lessons learned though. This is an important thing for you to take home, right? You can build an explainable model using PyMC2 and PyMC3. You can build a generative story. You can talk about this to your colleagues. Communication is the last mile problem of data science. And tomorrow we're giving a talk entirely on the last mile problem of data science. And PyMC3 is cool, so please use it and contribute it. If you want to learn more, these are the links that you need to know. I recommend you start with Bayesian methods for hackers. And this is my email. And that's it.
So, who has the first question? Hand up.
Oh, again.
Just on PyMC2, PyMC3.
Yeah.
Like, thought about switching. What do I need? What do I need to worry about, or what are the big things I should watch out for?
So the question is PyMC2 versus PyMC3.
What are the things you should worry about? Just the lack of examples and documentation is the only thing I would say. Sometimes Theano screws up with the computation graph and you have to clear your cache. That's one problem I've run into. But the functionality is just getting better and better. There was one thing that you weren't able to build good uncertainty estimates of your model, but that's been fixed since, right? So PyMC3 is getting better and better. So I would say move now in the same way as I would say move to Python 3 now from Python 2.
Yeah, you mentioned that the Bayesian approach has this advantage of that you're able to tell a story. Is there any other advantage you would like to point out as compared to a normal machine learning approach?
Well, I think it's good to have a different set of tools, and the more hammers you have, the better, right? So like rather than just using the one hammer. I think that for explaining things, it's very I've heard a lot of advantages for conversion analysis, like building models like of who will convert on a website. And that's what Cameron Davison Pylon uses a lot for at Shopify, an e-commerce outfit, because then you can explain the assumptions and explain and also build different simulations. People respond very well to simulations, I find, right? So they understand that the computer is doing something rather than you're just doing black magic and voodoo. Like, so.
Any other questions? We have time. Did
No,
you
I put money on
England?
Ireland and I lost.
Yeah, thanks for a fantastic talk. Just a quick one, I just like to know if you could tell me who's the absolute plonker who scheduled this great talk at the same time that the good rugby's going on.
I have no influence on how this was scheduled whatsoever. It is very much so.
Does anyone have a question not about the scheduling?
Yeah.
Any more questions? Well, there's no.
I just have a kind of a more general question about Bayesian statistics in Python. You showed us the example there, but is it possible to kind of port over traditional frequentist models of any description over to?
Yeah. So the question was, is it possible to port traditional frequentist models? And I interpret that question as meaning, is it possible to port like linear regression models, right?
Essentially, yeah. Can we do it in Python using some packages as opposed to having to hand roll?
So in PyMC3, and one advantage of it is that Thomas Vecchi wrote a bunch of model classes for like linear regression, right? So Bayesian linear regression. And from that, you get like all the possible answers, and you have like a spread rather than, you have a distribution rather than point estimates. And that's a really useful thing because that's what I use it for, right? So rather than using linear regression, I'll use a Bayesian linear regression. So you don't have to hand roll it at all. It's in the package.
Time for one last question. Yep.
How would you compare the scalability of machine learning as opposed to Bayesian learning?
Right, so that's a good question. How would I compare the scalability of Bayesian statistics versus machine learning? So,
For example,
but
random forests, for example.
well, I'm not sure if it's you're not really dealing with them. So some Monte Carlo simulations are embarrassingly parallel, so you can embarrassingly parallel them, right? But the other stuff in the models, I don't think so. I don't know about the putting it onto 4 cores and stuff like this. You do get some speed ups in some models and some you don't. I know that they've been talking about this and thinking about this, but why do you need to worry about this? Like, it's not a problem yet. Like, so, like, just rent a big, normal workstation and it should be fine, rather than worrying about clusters and stuff like this.